Hello friends, welcome to this new video. In this video we shall be discussing about the genesis of the base shear formula given in the codes of different countries. A general shape of the base shear formula is given here, what is corresponding to the Indian seismic code. So what is base shear? Let us try to understand what is base shear, then we shall go to further details. We have considered a building frame here having the masses M1, M2 and M3 at different levels. The masses are supposed to be concentrated at the floor level. Now if the mass M1 suffers an acceleration A1 due to earthquake, then the force that will be generated by Newton's law, the inertia force is 1 equal to M1 A1. Similarly, at the second floor level the force is F2 equal to M2 A2, and at third floor level it is F3 M3 A3, where A1, A2, A3 are the accelerations of the masses at the different floor levels. For the equilibrium of the forces, horizontal equilibrium, the summation of all the forces F1, F2, F3 must be equal to a resisting force here, which we are naming as BB, the base shear. So it goes like this, that this base shear BB equal to F1 plus F2 plus F3. Now if you want to compute the base shear through this formula, it will not be possible, because in the beginning you do not know the accelerations that the masses are suffering during earthquake. Not only that, the earthquake accelerations will be varying from time to time, and you don't know how to calculate a particular value of the base shear. So we need a empirical formula through which you can calculate the base shear, which will be dynamically viable, dynamically compatible, and which will be also useful for the design purpose. So what do you do with the base shear? The base shear that you calculate is then distributed over the height of the building at different floor levels, and the design is done for these lateral forces as the earthquake forces, along with the, of course, the vertical gravity force, whatever is there, dead load, live load and so on. So the forces are distributed over the floors in this pattern of this parabolic distribution pattern. Base shear into, for a particular ith floor, take the weight of the floor Wi and take the square of the height of that floor. For example, for the third floor, the height shown here is h3. And at the denominator you have the summation of all the weights at different floors and their height square, which are summed together. So this you can consider after you compute, this becomes a constant, and what is varying for the floor to floor for Qi, it is the weight at that floor Wi and Hi square and multiplied by base shear and this constant value at the denominator. However, in this video we are not interested in the distribution of the base shears, but how the formula have been arrived at, that we are discussing. But before going to the genesis of the base shear formula, let us see the base shear formulae available in some standard international codes. So here is Indian code, VB equal to Z by 2 I by R, SA by G, W. And EBC codes a very similar pattern, but with a little modification. R is common, here the T is the fundamental period, O it is same, CB is a constant, I is again impedance factor. So in this Indian code, let me read out the different parameters. Z is the zone factor, which indicates the seismicity level of a particular area. So whole country has been divided into 4 zones, zone 2 to zone 5. 2 is the lowest seismicity and 5 is the highest seismicity. The zone factors for Indian conditions are given as 0.1, 0.16, 0.24 and 0.36 for zone 2 to zone 5. R is the response reduction factor, SA by is the spectral acceleration ratio, and W is the seismic weight. Most of the parameters will be common in other codes also. UBC, impedance factor, is common. R is given a new name, ductility factor, and a new parameter T is introduced here, fundamental period. For the IBC 2006, the acceleration is given through the SDS, short period acceleration, and remaining parameters are same as in the Indian code. European code EC8 2003, the SDT1 value is the spectrum ordinate, vertical ordinate corresponding to the time period of the structure. And m is the total mass, lambda is a correlation factor. For New Zealand code, the formula is simple: C into WT. WT is the total weight and C is a coefficient. This coefficient C is given by another long expression which I have not shown here. So you can see that in most of the cases the pattern is same. The seismic weight is multiplied by a spectral acceleration value, and the value is reduced by a factor R, which is called response reduction factor or ductility factor. Now let us go to the genesis of the base shear, where from the base shear formula has arrived and how it goes. So we start from the Newton's second law, which says the force in a system is equal to the rate of change of momentum. Momentum is mass into velocity. So mathematically we can write F equal to d dt, differential of momentum m into velocity. Now here the velocity is changing with time, but mass is not changing with time. So mass is constant and can be taken out of this parenthesis. So we take mass outside and F equal to m dv dt. Now dv dt is the differentiation of the velocity with respect to time, which is nothing but acceleration. So we can now write force equal to mass into acceleration. So that is what is the second law of Newton. Straightforward we get like this. And this force now we shall name as base shear Bv. And so Bv equal to mass into acceleration. So you can see here if we have taken a single degree of freedom system, the mass at the top is m. So this mass is suffering acceleration of value a, and the corresponding force F is equal to mass into acceleration. This is acting from left to right. For horizontal equilibrium of force, another force has to act from right to left. So this is what is acting here, and this we are naming as Vv. So Vv equal to mass into acceleration is the most basic formula coming out of dynamics. Now let us understand what is spectral acceleration, which comes into play in the base shear formula. Spectral acceleration is the peak acceleration exhibited by a single degree of freedom system with some damping under a given earthquake. More details of this we may go into some other video. Here this much definition is sufficient, and the spectral acceleration is symbolized by the symbol S suffix A. So let us take these symbols here: m for mass, k for stiffness in this figure, and ut is the displacement response function. Displacement changes with time because earthquake is a time dependent force changing with time, so its response also will change with time. So ut is the displacement response function which is changing with time, and Fs say is the spring force, that is k into displacement. This k into displacement is the force which is the spring force or resistance force. So this also changes with time. You can write Fst, which is changing with time, equal to k into ut, changing with time. But k can be substituted from this expression. Omega, the angular frequency of a vibrating system, is given by k by m under root. So if you take k out, you get k equal to m omega square. So we are substituting this k in this equation by m omega square. So Fst, the spring force, becomes m omega square ut. So we go with this further and substitute this omega square ut by a new parameter Sat, and this is the spectral acceleration with respect to time it is changing. So substituting this, we get Fst, the spring force, equal to mass times spectral acceleration. So this is analogous to what we got by Newton's law. The lateral force was mass into acceleration. Now the acceleration definition and pattern we have changed. It is spectral acceleration, which is given by omega square ut. Both normal acceleration and spectral acceleration have the same unit, meter per second square, but the normal acceleration for a particular case and the spectral acceleration will not match in magnitude. Now for equilibrium of this single degree of freedom system that is shown in this figure, the resisting force Bv is equal to the spring force Fst, and the Fst we have seen from here is equal to mass times spectral acceleration. So we are substituting here mass times spectral acceleration. Now here we have shown BBT, which changes with time. The base shear is changing with time, and spectral acceleration also changing with time. Now let us consider a particular time instant. For that purpose, the variable t can be eliminated, and we can write VB equal to MASA for a particular instant. So this is the base shear formula, which is resembling our Cudell formula, mass times spectral acceleration. However, this will be further modified. Let us see in the next slide. So we started with VB equal to mass times spectral acceleration. Now mass equal to W by G. So we substitute this here. VB equal to W by G SA. Now W is a constant we can take on one side, and both spectral acceleration and acceleration due to gravity G have acceleration units, so we can take a ratio of these two. So now this is modified like this, VB equal to SA by G into W. So SA by G is called spectral acceleration ratio. The ratio of the spectral acceleration of the system to the acceleration due to gravity. And this is now most standard form, which is familiar, almost analogous with the Cudell formula of different countries. Now, the engineers thought this formula, if they use, then they will be missing something. What they will miss? If this formula is used for, say, Delhi and Assam, then it will not match with the acceleration seismic activity of the two regions. In Assam it is more, in Delhi it is less. So some more modifier to be applied over the formula. This is the modification of the formula we are considering. So one modification is the introduction of the different areas. So area we have taken up with the help of the zone factor. As we have discussed earlier, there are some zone factors associated with 4 zones in Indian seismic condition. In other countries, this is considered with respect to zone or with respect to the seismic control lines. Now, the Z is the zone factor, which is the highest possible perceived seismic level for a particular zone. Now, if I design all structures for this highest level, corresponding earthquake may not take place in the lifetime of the structure. So you shall design for a very large acceleration, and that the structure may not experience in its life. So it will be a wastage of material and cost. So what we do, we take half of this value. So now Z is now replaced by Z by 2, so that it is economical, as well as within the lifetime of the structure there is expectation that such level of earthquake may occur in the vicinity of the structure. Now all structures are not similarly important. A hospital building is more important than a residential building, and I may say my residential building is more important than your residential building. So something we have to do with the importance of the building. Some buildings will perceive as more important than others. So we introduce another factor, which is your I, importance factor. For Indian code, for normal buildings like residential building, value of I is 1, and for more specialized buildings like hospitals, bridges, it can be 1.5. Now something is still left. The building will suffer damage during earthquake, and because of damage, as we have discussed in our previous video, because of damage the force coming on the structure will be reduced. So the design force should be reduced accordingly, perceiving that there will be some damage. So we introduce a divisor here over this base shear formula, and this is your 1 by R, where R is called the response reduction factor. In some code it is called as ductility factor, and its genesis is remaining in the ductility arising out of the structure. So this formula now we shall rearrange and rewrite this way: VB equal to Z by 2 I by R SA by G W, and that is what is the formula given in Indian code. And most of the other codes, the SA by G W is there always, and the modifiers are different in different countries. Thank you very much for watching the video. Like and comment on the video and subscribe the channel. Thank you, and see you again in the next video.